Boa tarde a todos e todas, buenas tardes, good afternoon. Nós estamos aqui em mais uma sessão, né, a 56ª, número 56 do Seminário de EDP e Matemática Aplicada. E nessa tarde, hoje, teremos a presença, né, de dois jovens pesquisadores, o professor Duvan Cardona, que atualmente está na Universidade na Bélgica, ele é da Colômbia, e o professor Reginaldo Demarque, nosso colega da Universidade Federal Fluminense. Teremos os colegas Mauro Rincon, apresentando o professor Cardona, e o nosso conhecido Juan Límaco, apresentando o professor Demarque, Reginaldo Demarque. Então, prazer ter vocês aqui, e eu passo, então, a palavra para o professor Rincon. Por favor, Mauro.
Obrigado, Sandra. Bom, é um prazer apresentar um jovem pesquisador aqui da Colômbia, Duvan Cardona Sanches. Ele fez matemática pela Universidade de Duvan, em Cali, Colômbia. Ele esteve em Bilbao, na Universidade de Deusto, com supervisão, desenvolvendo um projeto com supervisão do nosso querido Henrique Zuazua. No momento, ele está terminando o doutorado dele na Universidade de Ghent. O Duvan é membro da Ghent Análise PDS Center. Ele foi nomeado membro vitalício da Sociedade Internacional de Análise e suas aplicações em computação, que chama ISAC. Em 2021, nomeado revisor científico do Ministério da Ciência, Tecnologia e Inovação da Colômbia. O Duvan, embora muito jovem, ele já tem, pelo ResearchGate, 114 publicações e 366 citações. Pelo Google Scholar, tem 94 trabalhos com 366 citações. Então, ele vai concluir ainda, com toda essa produção, ele vai concluir o doutorado em dezembro agora. E hoje ele vai dar uma palestra com o título de Control Theory for Diffusion Models on Compact Manifolds. Agora é você, Duvan, muito obrigado pela sua presença.
Muito obrigado. So, okay, so I will continue maybe in English. I will try to do my best then for you. Thank you very much, Professor Rincon, for this very kind presentation. We also would like to thank to Juan Limaco for this kind invitation. It's very nice, at least, to be in virtual form in Brazil. I hope to visit this very beautiful country the next year for the conference of the ISAAC, which is the international conference, the International Society for Analysis, Applications and Computations. So, well, today, like Professor Rincon says, I will talk about control theory for diffusion models on compact manifolds. So, this is the topic. I will present some spectral inequalities for eigenfunctions that are valid for eigenfunctions of elliptic positive pseudo-differential operators on compact manifolds. So here, these spectral inequalities were established in this preprint that you can see here is available on the archive. In particular, pseudo-differential operators on compact manifolds are continuous linear operators. One usually represent this algebra of pseudo-differential operators using three parameters: the order, which is M, and ρ delta, which are other kind of parameters that measure, in some sense, the growth of the derivatives of the symbols for these pseudo-differential operators. All these things I will introduce later. But just let me say that if you consider one pseudo-differential operator in one of these classes, we call this the classes of operators. M here is the order, and ρ and delta are parameters. So on compact manifolds, usually ρ and delta satisfy these inequalities that you can see here. Ρ and delta belongs to the interval 0, 1, and delta is less than ρ. And he wants that these operators belongs to a class which could be invariant under change of coordinates. This second restriction is necessary, which is that ρ is larger than 1 minus delta. Okay, So other thing that I want to present today is the same kind of spectral inequalities, but in the setting of compactly groups when one can remove this condition on rho and delta. This condition here, rho larger than 1 minus delta, is removed for these classes of pseudo-differential operators. In the case of compactly groups, because we will use other kind of construction of pseudo-differential operators. So in general, compact manifolds, we will use the classes defined by Hormander, but in the case of compactly groups, we will use some other kind of classes which were defined by Ruchansky and Turun. Okay, so just to summarize, we will present some spectral inequalities which are valid for elliptic pseudo-differential operators. For now, we can think about, let's say, positive elliptic differential operators on manifolds. And we have one, let's say, motivation to do this is that these spectral inequalities have applications to control theory. We are in a seminar of PDE and applied mathematics. This is our maybe main motivation, to have applications for these spectral inequalities in the setting of control theory. So well, why to work with compact manifolds or with compact groups in particular? Because Lie groups, we know, are manifolds with symmetries. Okay, in particular, compact groups are diffeomorphic to closed subgroup of the set of unitary matrices of order M. Here you can see the definition when the dimension is large enough. So you have that compact groups, and in general, Lie groups are very good manifolds with symmetries. There are some examples, of course, the commutative example, which is the torus, which is this Euclidean space. This is can be identified with this quotient. We have other kind of, let's say, compact groups, which like, let's say, linear Lie groups, group of matrices like SUN, SON. In particular, let's say, to work with Lie groups is very nice because they provide characterization for other kind of symmetric spaces like spheres. In particular, here you can see one diffeomorphism, which is very well known, the set of unitary, special unitary matrices of order 2. This set is diffeomorphic with the sphere. And well, so this is the setting. We have to think in Lie groups, manifolds with symmetries, or general compact manifolds. Okay. So well, now let me give you some introduction, some background about the kind of spectral inequalities in which I am interested, of the kind of inequalities of extensions that I will present later. To do this, let me mention this historical result from 1980 by Harold Donnelly and Charles Pfefferman. They proved in their celebrated inventions paper this doubling property in one. What says this inequality in one? Says that if you consider the, let's say, one compact manifold without boundary, and you consider there the Laplacian associated to the Riemannian metric, and you consider the set of eigenvalues and the set on the corresponding set of eigenfunctions, you know, you have the Laplacian on one compact Riemannian manifold. This operator is an elliptic operator. This is an operator with discrete spectrum. Here we denote the eigenvalue by lambda squared and the eigenfunction by phi. And then the Donnelly and Pfefferman inequality says that if you compare the L infinity norm of your eigenfunction in a ball of radius 2r, and you consider other concentric ball to this one with half radius, one ball of radius r, and you analyze and you compare the L infinity norm of these two eigenfunctions, then you can compare these two quantities. Here you add this term here, this factor here that corresponds to something proportional to the square root of the Laplacian. To this inequality, one usually calls to this inequality the doubling property of eigenfunctions of the Laplacian. Yes? To this inequality that allows you to compare L infinity norms of eigenfunctions in concentric, with respect to concentric balls of balls associated to the Riemannian distance. Okay, well, so this is inequality, maybe something that is interesting for some people is that Charles Pfefferman, the guy here, was a winner of the Fields Medal in 1978. So this is really a very fundamental result in geometric analysis of elliptic operators. So something that is important is that one can ask, okay, we have this inequality for single eigenfunctions. Maybe one question is if this inequality remains valid in the case of sums of eigenfunctions. So Jerison and Lebeau in 1996 proved this, proved that these questions is true, okay? In affirmative, these questions saying that the doubling property by Donnelly and Pfefferman also is true for the case of sums of eigenfunctions. So if you take, again, the Laplacian, the system of eigenfunctions, and you take linear combination of these eigenfunctions, and you compare here, let's say you take this span of these eigenfunctions and lambda square is the more biggest eigenvalue, then the supremum of the L infinity norm of your eigenfunction with respect to one ball of radius 2r, with respect to the L infinity norm of the same eigenfunction with one concentric ball of radius r, then you have this inequality here. You have this doubling property. But here you have one constant that grows exponentially, like the inequality by Donnelly and Pfefferman. And the exponential term here is like the square root, grows like the square root of the more biggest eigenvalue. Well, so very well, this is a kind of spectral inequalities in which we are interested, because in some sense, this inequality gives you information about the growth of the eigenfunctions with respect to the L infinity norm. But you can also ask if this question, if this inequality remains valid if you replace the L infinity norm by other kind of norm, like L2 norm or LP norms, okay? And then a result by Jerison and Lebeau, Lebeau and Robiano and Lebeau and Suazua, any of them maybe with different version, but that one can summarize in this inequality in 3, says that you can compare L2 norms of eigenfunctions in this way. If you take again one compact Riemannian manifold, in this case you can take the manifold with or without boundary, and you consider the corresponding spectral data of your Laplacian, the positive Laplacian here, lambda g square denotes the corresponding eigenvalue. Then for one function kappa, that is a linear combination of eigenfunctions, you have these inequalities between L2 norms. If you take, let's say, the L2 norm of this linear combination of eigenfunction with respect to the whole space, and you compare this quantity with respect to the L2 norm of your sum of eigenfunctions, this wave packet in one with respect to the L2 norm of one open subset, a small maybe open subset of your manifold, you will get this inequality. Something that is important here is that this inequality, the constant in this inequality is sharp. This is a maybe fundamental remark proved by Jerison and Lebeau in this paper. So the sharpness was proved by Jerison and Lebeau, and removing certain geometric conditions on the open subset omega were proved by Lebeau and Rubiano and Lebeau and Suazua. So well, why these two kinds of inequalities are important? Because they have applications in control theory. Okay, so you have, let's say, one non-empty open subset of omega of your compact manifold, which can have boundary or not. Then if you consider the heat equation associated to the Laplacian, then here, then you have on the left-hand side, you have the standard heat equation, but on the right-hand side, you localize one input function with respect to the characteristic function of your open subset, and you have one initial condition. So one question in control theory is to say when this, which are the conditions on this set omega that allows you to drive the solution to 0, let's say, in some time. So you say that this heat equation is not controllable at time t. If, let's say, for any initial condition, there is one input function G in L2, such that the solution to this heat equation in time t is null. Okay, when this happens, then you say that this diffusion model is null controllable. So well, Levaux and Roviano proved that the condition that you need to make this diffusion model null controllable is just that the initial condition belongs to L2. Okay, so Levaux and Roviano proved this statement, that is the null controllability of the heat equation. This is a very famous result published in Communication on Partial Differential Equation. And then for the proof of this null controllability result, Levaux and Roviano use this inequality in tree, this inequality for this kind of wave packets of eigenfunctions. So well, summarizing, we have this L2 norm, inequalities between L2 norm of sum of eigenfunctions, wave packets of eigenfunctions. We have this L infinity inequality also for sum of eigenfunctions, and we have the null controllability of diffusion models in this way. And this inequality plays an essential role in the proof of this null controllability, the null controllability of the diffusion model. So well, so maybe some remarks now about the proof of this inequality in tree, of this spectral inequality, and is that for the proof of this inequality, one uses strongly the validity of Karleman estimates for the Laplacian. I will not talk about of Karleman estimate, but just let me say that this is an essential analytical tool in the proof of this spectral inequality, but this depends on the locality of the operator, in this case of the Laplacian. Yes. So if you ask, let's say, if this inequality here, this spectral inequality is valid for other non-local operators difference of the Laplacian, let's say non-local operators like powers of the Laplacian, then if you want to prove this kind of inequality, you don't have the essential tool, which is this Karleman estimate. So now it's natural to ask if this doubling condition, or if this inequality in tree is valid for more general operators difference of Laplacians on manifolds. And then this is our motivating problem. Here, this will be our three main questions for this talk. We will solve these questions at the end of this seminar. The first one is that if the Levaux-Roviano, Jerison-Levaux, or Levaux-Soissois spectral inequality is valid for more general operators of the Laplacian, which are positive, let's say, elliptic pseudo-differential operators, so arbitrary compact manifolds, even manifolds with boundary. The second question is if the Donnelly-Pfefferman spectral inequality also remains valid. And the third one is that if the null controllability for the corresponding diffusion model is valid. Here, EXD is one pseudo-differential operator. I will introduce these operators later. Okay. Here, kappa represents some of eigenfunctions for this operator. I put these three questions in this order because essentially one can prove that the inequality in 8, which is the inequality for L2 norms, implies the inequality in 9 for L infinity norms. And also the inequality in 8 implies the null controllability for the diffusion model. Okay. So the proof that 8 implies 9 is a very nice, let's say, a very nice application of the Sobolev embedding theorem. Okay. So here the more important thing is to prove the extension of this inequality in 8. Okay. So well, because pseudo-differential operators are general operators, and also you can have arbitrary classes of manifolds with boundary or without boundary, then I will be more precise in my question. Which kind of manifolds, in which kind of manifolds I am considering the corresponding pseudo-differential operator? In manifolds with boundary, manifolds without boundary, or manifolds with good symmetries, like compact Lie groups. So in this talk, I will just talk about general compact manifolds without boundary and manifolds as a class of this kind of manifold, which are compact Lie groups, which are manifold with symmetry. So in this context, I want to solve these three questions. Okay, well. So a short overview about pseudo-differential operators is the following. On Rn, these were linear operators defined by Kohn and Nirenberg in 1965 and by Hormander in 1967. For the definition of pseudo-differential operators, the essential tool is the Fourier transform. So here you have the definition of the Fourier transform in this integral way. You take one good function, let's say L1 function, and then the Fourier transform is defined in this way. And then here you take one function, sigma on Rn cross Rn, sigma xi, one measurable function. You define the corresponding pseudo-differential operators associated to sigma A in this way. One motivation to do this is that for any continuous linear operator on Rn, you can associate one smooth function or one distribution, sigma A, satisfying this integral inequality. So this integral representation looks a little bit general, but any continuous linear operator have this representation. In particular, partial differential operator has this representation. If you talk, let's say, about partial differential operator, then this function here, which is called the symbol, is just a polynomial in the psi variable, okay? So, well, the motivation for Kohn and Nirenberg to introduce this algebra of pseudo-differential operator was the invertibility of elliptic problems, like invertibility of the Laplacian of manifolds and these things. And then they classify the symbols of the algebra of pseudo-differential operators by the growth of the derivatives. So here you will see three fundamental parameters. M, which will be the order of the symbol, and rho and delta, which tell you about how the derivatives of the symbol with respect to the variable psi or with respect to the spatial variable behaves. You see here in the definition that by Hormander, let's say, introduced in 1978, that he will classify symbols in this way. So you take, let's say, derivatives with respect to the frequency variable, then you have one decay in terms of rho here, and you take derivatives with respect to the spatial variable, and then you will allow one growth here in terms of this parameter. So remember, M, rho, and delta are these three fundamental parameters that will be fundamental for us for the classification of pseudo-differential operators. You have also pseudo-differential operators on the torus. You can make the mimic of the definition here, this integral definition on Rn, but in the set of integers you have let's say Fourier coefficients. In the set of the torus you have Fourier coefficients. Remember that functions on the torus, or functions in this space, are periodic functions in each variable, and then these are functions defined in the cube 0,1 with the power n. And then you can define for these functions Fourier coefficients. And then any continuous linear operator on the torus admit this representation in sum, this discrete representation that you can see here. And this in this setting, the symbol is a function defined in Tn cross Rn. Okay, so you can define classes of symbol also, allowing this allowing the validity of this inequality. You take in this case, you take the symbol because the second variable is discrete. Then you will not take derivatives. You will take differences, the standard differences in the lattice. And you take derivatives with respect to the x variable, and then you will classify this class of symbols by the order, which is rho and delta. Okay, well, so this definition on Rn and on the torus essentially follows the setting of Kohn, Nirenberg, and Hormander. But on compact Lie groups, you can make a different description using the Fourier analysis of compact Lie groups. On compact Lie groups, you have representations. On compact Lie groups, then you have a Fourier analysis. And in company group, you have then a Fourier inversion formula. And using this Fourier inversion formula, you can define pseudo-differential operators. So you have, let's say, one company group. You have a jihad here, which is the unitary dual of one company group, which is the set of unitary and irreducible representations of the group modulo equivalent classes. And then you can define the Fourier transform. In this way, you define the Fourier transform, okay? And then the corresponding pseudo-differential operator associated to one symbol is defined in this way. Because here psi is a representation of a company group. These are usually representations on finite dimensional spaces. So C of X in general is an endomorphism on a let's say a vector space of finite dimension. You can identify this object with a matrix, and then you can think about the Fourier transform of your function like a matrix valued function. Okay, so the Fourier coefficients in the setting of company groups are matrices. So the symbol also has matrix valued values. The symbol is matrix valued, and then you take trace here. You take traces to recover operators. So something like in the case of Arena and the torus, any continuous linear operator on a company group admit this representation here. You can associate a symbol, and then you also can, let's say, classify symbols by using differences, like in the case of the torus, by using derivatives with respect to the x variable. But we are in the case of a company group, so you do these derivatives by using vector fields, okay? And here are some parameter psi, which is enumerated by the spectrum of the square root of the Laplacian. Yes, this is the analog of this psi here, bracket psi here, and this bracket psi here that you define in terms of this quantity. Okay. So well, this is just a short overview about pseudo-differential operators on compact manifolds. Let me give you a more precise definition. You have, let's say, one open subset of Rn, and then you define symbols on this product space, you cross Rn. You will say that one symbol belongs to this class, a sem rho delta class on this product space with rho and delta satisfying this inequality. Here, for any compact subset key in U, you have the validity of this spectral of these inequalities here, okay, of these symbol inequalities here. So here you can see the role of the order and the role of rho and delta, yes, that allow you to define these classes. If this happens uniformly in compact subset of your open subset U, then you will say that this A is a symbol in the sem rho delta class. So once you define symbols, then you can define the corresponding pseudo-differential operators in this integral way. You put here the symbol, you multiply it by the Fourier transform functions, and then you take the inverse Fourier transform, and in this way you define pseudo-differential operators associated to this symbol. Okay? So in this way you define symbols on open subsets of Rn. Even if U is equal to Rn, this definition is valid. And you have the definition of pseudo-differential operators. Like I mentioned you, the main tool here is the Fourier transform. And then once that you define these symbol classes on open subset of Rn, you can define these classes also on manifolds, because you can localize these operators. Okay, so if you take one compact manifold M, you say that one continuous linear operator between these two Frechet spaces here is a pseudo-differential operator of order M and of rho delta type, but with this restriction, rho larger than 1 minus delta. If in every local coordinate path, when you localize your operator A in this way, you get one continuous linear operator, but now acting in a smooth function some sonopet of some Euclidean space, okay? And then when you localize this operator, if you see this operator by using local coordinate systems, then you will say that this operator belongs to the Hormander class of order M and of rho delta type, if when you localize your operator has a symbol that belongs to these classes, okay, ejemplo de esta, on open subset of your chart. Okay, something important here is that when you define symbols on Rn, you can define operators, but if you define pseudo-differential operators on compact manifolds, the symbol is a section of the cotangent space, and then is a invariantly defined element, is a well-defined section, only if rho is larger than 1 minus delta, okay? So the symbol is unique, has an element of this quotient algebra here, okay? So let's think about the symbol like a unique element in this quotient algebra, whose argument belongs to the cotangent space of your manifold, and that the local coordinate system has this integral form. So this is a short overview about pseudo-differential operators on manifolds. Here we go to, let's say, to company groups. One can make an alternative definition of pseudo-differential operators without using local coordinate system. If you see pseudo-differential operators on company groups. And this was an approach introduced by Michael Ruchansky and Billy Turunen in 2006. So the thing is like follow. To define pseudo-differential operators on company groups with symbols that are not defined by local coordinate system, you need a globally defined Fourier transform. And to talk about Fourier transform on company groups is like to talk about representation theory of company groups, okay? So let's say you have one unitary representation, which is a map, which here we denote by psi. You say that this representation is unitary if at any point of your group, G here is a company group, C of x star, which is the adjoint of the transpose, it's yet simple, okay? In this way, you say that this map psi is a unitary representation. And then this unitary representation is irreducible. You cannot write this like the direct sum of other two unitary representations. So examples of these mappings are like, for example, in the torus, representations are just exponentials. But in general, company groups representations are not necessarily scalar valued, like in the case of the torus. In general, on company groups, non-commutative company groups representations are matrix valued, okay? Because the compactness of the groups imply that the dimension of this representation space H psi here is of finite dimension, okay? So you can, for any x, you can think about C of x like a matrix. So well, you take, let's say, one company group and define the unitary dual of G, which is G hat. Like I mentioned before, this is the set of all the continuous and irreducible unitary representation of the group. You can define Fourier coefficients of L1 function of G. On G, you have the hard measure because we are talking about a group. Then we can think about the Lebesgue spaces. You take one function in L1, and then you can define Fourier coefficients in this way, okay? So think about that for any function in L1, the Fourier transform is a matrix valued function. Yes, this is important. So this is a good Fourier transform. You have Fourier coefficients, and then you have the Fourier inversion formula here, which allow you to recover the function using the Fourier transform in terms of the sum. Something that is special is that if G is a company group G hat, the unitary dual of the group is a discrete set, and then you have this Fourier inversion formula in terms of the discrete sum, okay? Something of Fourier analysis here is that for this Fourier transform, you have the Parseval identity, and you have here the Plancherel theorem, okay? Here you take trace for Parseval, you take here trace of matrices, but for the Plancherel theorem, you take here the Hilbert-Schmidt norm of matrices, okay? Okay, well. So maybe let me skip a little bit here because I am more or less over the time. So let me skip. Let me just go to this point. Is that if you consider one continuous and linear continuous and linear operator on a company group mapping a smooth function to distributions, you can associate to this continuous linear operator one matrix valued function, where the first variable belongs to the group, but where the second variable belongs to the, is one representation, belongs to the unitary dual, modulo equivalent classes, belongs to the unitary dual. And then you can associate to your operator this matrix valued function in such a way that your operator satisfies this identity here in the yellow box that you can see. Here is the operator, and here this matrix valued symbol. Remember that this is different to the approach by Hormander, when you define the symbol using local coordinate system. In this way, you have a globally defined symbol, but you are using representations to define this matrix valued function, matrix valued symbol. Okay, so, well, maybe let me go to the main results. But maybe I need the definition of ellipticity of pseudo-differential operators. Let me do this quickly. On a compact manifold without boundary, you take, let's say, one pseudo-differential operator of order M and rho delta type, and you will say that this operator is elliptic of order M if in any local coordinate system, when you look the symbol of this operator, the symbol is invertible far from, let's say, the zero section, okay? And satisfy this inequality in 11, okay? So you have this growth for the symbol, okay? In some sense, for, let's see here, theta is the second variable of your symbol. For theta far from zero, you have this kind of inequality. This in particular gives you invertibility of the symbol far from zero. So we can think about ellipticity like invertibility of the symbol of far from zero and satisfying this inequality. And on compact groups, because you associate to one continuous linear operator one symbol, which is a matrix, then you can think in the same way. You say, okay, your symbol, your operator is elliptic if the symbol, which is matrix valued, is an invertible symbol in any representation space. This says that in any representation space, the symbol, which is a matrix, is invertible for almost all the representations, okay? Because remember that the second variable of the symbol in the setting of compact groups is discrete, okay? It's one representation. And satisfying this group, okay? So here we have the definition of ellipticity in the setting of compact groups and in the general setting, the first one by Hormander and the second one by Rubchansky and Turunen. And then let me go back to the main part of this seminar, which is to present the extension of this initial spectral inequality by Pfefferman and Donnelly and by Duvan Cardona in the setting of pseudo-differential operator. So the main results are the following. If you have, these are main results. If you have then one pseudo-differential operator of order nu here, I take one positive order here, which will be a real order. Then if you take one pseudo-differential operator of positive order nu, which is elliptic, and for example, the symbol defined by localization, defined by local coordinate system of this operator is strictly positive, then for any open subset of omega, you have this spectral inequality like the inequality by Jerison and Duvan Cardona for some of eigenfunctions of this operator. Remember that if you have one elliptic operator on a compact manifold, the spectrum of this operator is a discrete set, then you have a discrete system of you can consider a discrete system of eigenfunction that provide that orthonormal basis of L2M, let's say, of L2. And then we have the validity of this inequality. See here that the corresponding eigenvalue is lambda with the power nu, but then in this constant here, this factor, when you compare these two L2 norm, this factor is almost of exponential growth, and here appear lambda, okay? So if you consider this linear combination where lambda with the power nu is the more biggest eigenvalue, so here appear the new root of your eigenvalue. So in the case, of course, of the Laplacian, we recovered this theorem by Lewan-Suazua and the theorem by Jerison and Lewon. And something that is special here is that using this inequality in 12, we can say something about the inequality. We can prove a similar inequality like the one by Donnelly and Pfefferman. And this inequality looks like this. You have one, let's say, radius R, and you define the corresponding volts associated to the geodesic distance in your manifold. And then when you take the infinity norm of sum of eigenfunction with respect to concentric volts of radius 2R and R respectively, then you have this estimate here. And this factor grows in the same way in which grows the Donnelly and Pfefferman, the doubling property by Donnelly and Pfefferman. Okay. So here the condition, see that the condition that we have is a condition on the symbol of the operator. Yes, this positivity condition of the symbol of the operator. If we have this positivity condition of the symbol, then we have this spectral inequality for the system of eigenfunctions. Okay, and then in view of this inequality, by following the philosophy by Lewan-Suazua, one can prove also the null controllability for diffusion models for arbitrary elliptic operators. Let's say if you take one pseudo differential operator of order nu, and you take powers here, 1 power alpha of this operator, and you see the corresponding diffusion model, then one can prove that if the symbol of the operator is strictly positive, then this model in 14 is null controllable. Remember that this means that for any time, here you fits one open subset omega for any time, you can find for a given initial condition a solution such that in capital time t, the solution vanishes. Okay, the solution is null. Okay, well, and in the setting of compactly groups, see here that because we are talking about pseudo-differential operators on general manifold, we have always this restriction, rho larger than 1 minus delta. But in the setting of compactly groups with Michael Ruchansky from Ghent University and Julio Delgado from Cali, Colombia, we remove this condition in the setting of compactly groups using the matrix valued symbol. So if we take one pseudo-differential operator of order M and of rho delta type, and we assume that this operator is positive and elliptic of positive order, then if the symbol is positive, because look at here, because your symbol is matrix valued, then you can talk about the positivity of matrices. Then if you assume that in any representation space, your symbol is a positive matrix, then you have the validity of the Lewan-Suazua spectral inequality and the Donnelly-Pfefferman spectral inequality in 15 and 16. Of course, here, AG and lambda G with the power M represent the spectral data of your operator, and you have this for this linear combination of these eigenfunctions. Okay, these are analogs of the Lewan-Suazua and Jerison and Lewon results. And then we have, as consequence of this spectral inequality in 15, we have the null controllability of this problem also in the setting of compactly groups when we remove this condition rho larger than 1 minus delta, just by assuming the positivity of the matrix valued symbol of the operator. Okay, so well, maybe just let me say that to finish, that this problem that we address here for the setting of compact manifolds and compactly groups is still open for general pseudo-differential operators on manifolds with boundary. Even in the case of these powers of the Laplacian with suitable boundary conditions, the problem is still open. This is an open problem that was addressed by Rousseau and Roviano in this recent paper published in Journal of European Mathematical Society. So if you are interested in proving spectral inequalities on compact manifolds with boundary, here you have one open problem. So, well, maybe I am over the time, so thank you maybe thank you very much for your attention.
Obrigado, Duvan. Parabéns pela sua palestra. Agora estamos abertos para perguntas. Alguém tem alguma pergunta a fazer ao Duvan? Alô? Bom, Duvan, vamos, enquanto alguém faça alguma pergunta, eu vou fazer uma pergunta curiosa aqui, tá?
Okay,
eu não sou da área, mas eu gostaria de saber o seguinte: essa relação que você tem do W, da função característica, você disse que aquele conjunto basta ser não vazio e tá contido num corpo lá, né? Agora, se esse conjunto tem a ver, qual é a relação que existe entre o tamanho desse subconjunto aí e o tempo para você controlar essa equação de calor? Existe alguma relação, não?
Okay, here we don't have, I suppose. We have here we don't have so much restrictions about the set, okay? About the set omega. We have that I can say about this set omega is that omega can be small enough, so small that you want. In the case where omega is equal to the complete manifold, then you have for free the uncontrollability of the problem, because you can do this by Hamel principle. But there are some people that are interested in removing conditions on omega. Let's say to consider, because here I always consider omega to be an open subset, but there are other people that remove these topological conditions on omega. Say there is some people that is considering omega to be a measurable set, just a measurable set. That is the case of recent works by Escauriza, Herbert Koch, many people that is removed. So about the size of the set, here we allow the set to be, omega to be small enough or big enough, even the complete manifold, but we have this topological restriction, okay, that omega is open, okay?
Thank you, Duvan. Someone a question? No more question in this moment. I hope is in future you have contact with many people.
Okay.
Thank you, Duvan. Muito obrigado. Graças. Até a próxima. Muito obrigado, tá, Duvan? Sandra.